Welcome back to Year 11 Methods with me, Mr. Hanna. Today we're going to be starting on our power functions, and we're starting with the hyperbola, or more specifically the rectangular hyperbola. Okay, now the hyperbola is a function that basically looks like this. It's the function of x, looks like x to the power -1. Now, hopefully you remember from your index laws, that's the exact same thing as 1 over x. Now, if we want to plot this, the function of x equals x to the power -1, and we have absolutely no idea what it looks like, we can always just make a table of values and fill it in and plot the points and join the dots. Okay, so that's the best way to go if you ever don't know how to plot something. Just make a table of values. So pick some x values and figure out what the function looks like for those values. So let me just do that for you now. Okay, so I've chosen to go from -4 to 4, and I've also included a couple of points that are going to be decimal values between 0 and -1, or between 0 and 1. So I've put in a half and a quarter. It's always a good idea to do that, because sometimes you get some strange behavior in there. So if we put in x equals -4, we get 1 divided by -4, so that is of course -1/4. And similarly here with -3, we get 1 over -3, which is -1/3. And I'll just quickly fill in these ones, -1/2, -1. Now here when we get to this value, a strange sort of behavior happens. We have 1 divided by -1/2. So 1, how many halves? Well, it's obviously 2 with a -2. And similarly with 1 divided by -1/4, gives us -4. Now, a strange thing again happens at 0. You can't have 1 divided by 0. You just cannot have it. It is undefined. Undefined. It is a big no-no. Do not put x equals 0 in there. It's not allowed. Okay, now these values are basically just the same as the other ones, but they are no longer negative. So here we've got 4, then 2, 1, half, third, quarter. Okay, so now I'll set up a set of axes. Right, here's my set of axes. Now I just need to put all these points in. So I'll start from this end and I'll move backwards. Okay, so when I put in x equals 4, I get a quarter. So 4 is about here. X equals 3, I get a third. So that's a bit bigger than a quarter. X equals 2, I get a half. That's a bit bigger again. Put in 1, I get 1. 1. Put in half, I get 2. Put in a quarter, I get 4. Quarter, 4. 0 is undefined, so I'm going to put a dashed line here to show that it does not hit the y-axis, and it will never actually hit, because even if I go a fifth, then it will just go up to 5, and if I put in a sixth, it will go up to 6. It will just keep getting closer and closer to the y-axis. It will never actually hit it, because when I put 0 in, it's undefined. Okay, now for the other side, when I put in -1/4, I get 4. It's way down here. When I put in -1/2, I get 2. Put in -1, I get -1. Put in -2, I get -1/2. Put in -3, I get -1/3. Oops, negatives. Put in -4, I get -1/4. Okay, so now I'll join up these lines, these dots, sorry, with a line. Show what this looks like. So there we go. It will look like that, and that is a hyperbola. Now, a couple of very important points to point out. A couple of key points here. This is 1, 1, and over here we've got -1, -1. That's kind of interesting. It's also symmetrical, and the most important thing is that it never ever will touch the y-axis or the x-axis. So I'll use some dashed lines to show that. Because it never touches those, we give these things a special name. When the values will approach them, it'll get closer and closer at these extremities here. It'll get closer and closer to the x-axis over here, and closer and closer to the y-axis. But without touching them, we call those asymptotes. There you go, asymptotes. So that's the word of the day, word to remember, asymptotes. And they are very, very important. Now, with hyperbolas, we can actually do our regular dilations and translations and reflections. We can do those just as we would any other time. So let's. So we're going to have a quick investigation on the functions of x when it's got a few bits and pieces. Okay. So it will look like this, and of course you know from your index laws that's actually the exact same thing as if we wrote it in this way. Okay, so I think you've probably spotted that I've used the same symbols. That's because these things do the exact same thing. Now my preferred way of writing this is like this, because that's exactly the way we would write a quadratic in vertex form, except we've got a -1 here rather than a squared. But basically the dilation, the translations, and the reflections, they all behave in exactly the same way. But let's have a quick investigation of those on our calculator, and then I'll do an example to finish this off. Okay, so I'm going to start by just plotting the most basic hyperbola. So I've got x to the power -1. There we go, I've plotted the most basic one you can get, and you can see the shape of it is the same as what I have shown. Now let's start by looking at the dilation factor. So let's do a graph of 2. Oh, whoops. Need to. Alright, so let's plot a new graph. So we'll do this time 2 times x to the power of -1. So here we've got a dilation factor of 2, and you can see how it is dilated. So there we go, it's been a little bit dilated. Now let's check out what happens if we use some translation. So first let's have a look at the translation of k. So first perhaps I will undo that graph that I put in. Now let's put in another one. Let's put in x minus 1 to the power of -1. So here I've set k to 1, and you can see what's happened. The graph has shifted to the right 1 unit. So it's shifted to the right 1 unit. Not very surprising. Let's undo that. Oops. Undo that. And now we'll look at k. Let's put in x to the power -1, and then we'll add, say, 2. Whoops. Gotta remember to go down off that. So add 2. There we go. It's just been shifted up 2 units. So what's happened here is the asymptote itself has actually shifted, even though it's not shown here. Okay, now let's get rid of that. Last thing to investigate. Whoops, keep doing that. Last thing to investigate is a reflection. So we'll pop in minus x to the power -1, and you can see it's just been reflected in the x-axis. Okay, so let's combine all of those things now and see what we get. So let's give ourselves a question of sketch. So let's make it hard. Why not? Sketch f of x equals -3x minus 1 plus plus 2. There you go, we'll sketch this. Now, of course, you remember this can be written in an alternative way. It can be written -3 over x minus 1 plus 2. So just keep that in mind as well. Keep that alternative method in mind. I'm going to stick with this because I think it's more clear, at least for me. Okay, so first thing I'm going to do is locate my asymptotes. Now here my k value is 1, so it's been shifted to the right 1 unit, and here my h value is 2, so it's been shifted up 2. So I'm going to sketch those things in first. X, y, so it's been across 1. So this asymptote is now here, as it's been shifted across 1, and up 2. So the x-axis asymptote is actually here at 2. So there are our two asymptotes. Now you don't always have to write asymptotes, I'm just writing it so that you can keep this word into your mind. Okay, so there are our asymptotes. Next thing I notice is I've got a negative sign out the front, so it's been reflected. So I know that the general look of it is something along these lines, as it's been reflected across the x-axis. Now all I need to do now is to show that it has been dilated by this factor of 3. So to show it's been dilated, I need to put at least 1 point on this section and at least 1 point on this section. I also know though, for whenever I sketch any graph, that I should always show the axis intercepts. Now luckily here I've got an axis intercept in both sections. So if I just show the axis intercept, that will be also enough to show this dilation. So let's first look at the y-axis intercept. That is when the x value here is 0. So let's put x equal to 0 into our equation and see what we get. So we're doing the function of 0 here equals minus 3, 0 minus 1 to the power minus 1 plus 2. So that's minus 3. Now 0 minus 1 is minus 1. Minus 1 over minus 1 is, of course, minus 1 plus 2. Minus 3 times minus 1 is 3 plus 2, and that equals 5. So this point here is 5. Or if you were to write it as a coordinate, it's 0, 5. So there's that point there. And now over here, we're looking for the x-axis intercept. This is when y equals 0. So here we're doing 0 equals minus 3 x minus 1 to the power minus 1 plus 2. So first I'll take the 2 to the other side, minus 2 by subtracting 2 from both sides, minus 3 x minus 1 to the power minus 1. Now I'll divide both sides by minus 3, 2 on 3, x minus 1, power minus 1. Now here I've got to undo the power minus 1. Now to undo x to the power minus 1, so we've got to undo x to the power minus 1. The way to undo it is to do a minus 1 again. And here's the reason. So it undoes it. So in other words, you get x out. Here's why. If we've got the first minus 1 sort of flips it, if you like, makes it the reciprocal, and the second one flips it again. So the second one flips it again, which sort of does like a, you can think of it like doing 1 over 1 minus x, if you want to. But it basically flips it again, so you've got x over 1, which is just x. So here, to get rid of the minus 1, I'm going to do to the power of minus 1 to both sides. So 2 over 3 to the power of minus 1 undoes it, giving us minus 1, x minus 1. Now this one, it sort of flips it, as I mentioned, so that's 3 over 2 equals x minus 1. Now I'll add 1 to both sides, 3 over 2 plus 1 equals x. Now I'll write the one, I'll just shift over here. So it's 3 over 2. Now I'm going to write 1 as 2 over 2. Because now x equals 3 plus 2 is 5 over 2. So this value here is 5 over 2, or written like coordinates, 5 over 2, 0. And there we go, we have fully completed this sketch of this hyperbola.